Okay, let's zoom in on the architecture of, well, the internet's nervous system.
That's a great way to think about it.
Today, we are undertaking what I think is a pretty critical mission, diving deep into the very core logic of how networks think, how they strategically map their surroundings, and how they decide the single absolute best way to route data from any given source to any possible destination.
Right.
This isn't just about simple forwarding. It's about network strategy, detailed cartography, and high-speed consensus.
And this is foundational. We are talking about Open Shortest Path First, or OSPF.
OSPF.
For any learner looking to truly grasp the internal logic of a large network, what's known as Interior Gateway Routing OSPF it's the central protocol. The sources you've shared are a phenomenal guide.
They really are.
They lay out the protocol's architecture, its specialized language, the LSAs, and the complex strategies it employs to manage massive scale.
Our mission today is to take this intricate diagram of networking protocols. I'm talking about the complex states, the multi-tiered areas, and all those acronyms, and distill them into actionable, crystal clear understanding.
I like that.
We're going to focus on the core mechanism of how OSPF judges quality, the precise choreography of neighbors becoming friends, and why OSPF has fundamentally earned the title of the network mapmaker.
And that mapmaker concept isn't just a catchy phrase. It really speaks to the protocol's core philosophy. Understanding OSPF fundamentals, especially the centrality of its link state database, its cost metric, the 7 states of adjacency, and its sophisticated area configuration, is truly understanding network scaling, path optimization, and resiliency.
So let's jump right into the data.
Let's do it.
So let's start with the basics. What exactly is OSPF? I mean, we know it's a protocol, but what makes it different in philosophy from, the older ways of writing?
What's fascinating here is that OSPF is defined as an open standard link state routing protocol. The open part means it's universally available, not owned by a single vendor, which is great, but that link state designation is the critical philosophical differentiator. It uses Dijkstra's shortest path first algorithm, a highly efficient and deterministic algorithm to find the optimal routes across the network.
The implication being that it differs sharply from, say, a distance vector protocol.
Absolutely. Think about how knowledge is distributed. In a distance vector protocol, like the old RIP protocol, for example, a router only trusts the information its immediate neighbor tells it.
It's like a rumor mill.
It's a system of secondhand knowledge, a rumor passed down the line. A router might say, I can reach that destination in 5 hops because my neighbor told me so. It has no idea of the quality of those 5 hops or the actual path taken.
So it's trusting the gossip of its neighborhood rather than possessing a confirmed objective view of the entire city map.
Precisely. That inherent limitation leads to slower convergence. If a path fails, it takes time for the rumor, the distance vector updates, to propagate across the network.
And that can lead to routing loops.
Huge routing loops and downtime. OSPF flips this entirely. OSPF routers, by definition, insist on having their own comprehensive data set. And this brings us directly to the core identity outlined in the sources. Every router is a mapmaker.
Okay, let's unpack that map-making identity, because that's the crucial shift. The source states that every router builds its own complete link state database, the LSDB.
The LSDB is the complete network map. It contains every detail about every router, every link state, whether it's up or down, and the cost associated with that link within the OSPF area.
That's incredibly detailed.
Imagine you are running a complex logistics operation across a continent. Would you rather rely on 5 drivers calling in partial directions?
No way.
Or would you prefer that every single driver has an identical high-definition GPS map of every road condition, every bridge closure, and every traffic jam?
The GPS, obviously.
The OSPF router takes the latter approach.
The genius of this decentralized but identical map is the ability for calculation, right? If I have the full map, I don't need to ask anyone where to go.
Exactly. Because each OSPF router possesses this full LSDB, it runs the Dijkstra algorithm against that data, calculating independent, loop-free paths from itself to every other destination within its area.
So it builds a tree.
It essentially constructs a shortest path tree, or an SPT, where the router running the calculation is the root of the tree. This guarantees the most efficient and reliable path is chosen. This comprehensive map is the foundation of OSPF's reliability, and its defining feature of fast reconvergence.
Let's explore that resilience a bit more. We asked earlier, why is having a complete map better than just knowing the next hop?
The difference is speed and intelligence in the face of failure. It's huge. If a distance vector router's next hop fails, it needs new information from its neighbors, which takes time.
That's the rumor mill slowing down.
Right. But if an OSPF router's link fails, that router already has the full map, the LSDB. It instantly identifies the failed link in its own database, it prunes that branch from its shortest path tree, and recalculates the entire tree instantly to find the next best path to every destination. This ability to almost instantaneously adapt to topology changes, that fast reconvergence, is what makes OSPF paramount for minimizing network downtime in large-scale environments.
So if they're all map makers, they need a common objective standard for judging the quality of a road. In OSPF, that standard is the cost metric. It's not just about how many routers you jump through.
No, not at all. It's an intelligent metric focused on capacity and speed, not hops. OSPF uses a weighted calculation. The lower the cost value, the better the path.
And it all comes down to that simple formula.
The cost metric is calculated using that crucial, simple formula: cost, reference bandwidth, interface bandwidth.
Let's break down the implications of this formula. It's prioritizing superior bandwidth over minimizing the number of devices you cross.
Precisely. Imagine a data packet needing to travel from New York to Los Angeles. Path A uses 3 hops, but each link is an old, slow T1 line, maybe 1.5 millilps.
Not great.
Path B uses 7 hops, but every link is a brand new fiber 10 Gbps connection. OSPF will assign a vastly lower cost, a much better rating to Path B, despite it having more hops, because its bandwidth is superior.
That makes so much sense.
This formula fundamentally engineers the network to incentivize and utilize higher capacity links, leading to better throughput and lower latency for the data.
That makes perfect sense from an engineering perspective.
Yeah.
But the formula relies on that mysterious component.
Right.
The reference bandwidth.
Right. The reference bandwidth is the baseline, the yardstick against which all interfaces are measured. Historically, when OSPF was developed, 100 megabits per second was considered a very fast link.
So that was the default.
The default reference bandwidth was often set to 10 to the 8th bits per second, so 100 millibits.
Wait a minute. That sounds like a potential point of failure due to human error. If the network engineer forgets to adjust that reference value, particularly in modern high-speed networks,
It can cause huge problems.
OSPF loses its ability to accurately judge link quality.
That is absolutely correct, and it is one of the most common pitfalls for network engineers. If your reference bandwidth is set to the default 100 megabps, OSPF will calculate the cost of a 100 megabps link as 1.
Okay.
Crucially, it will also calculate the cost of a 1 gigabit link, 1000 mbps, as 1, because the formula dictates that the cost must be rounded down to the nearest integer, and it will calculate the cost of a 10 gigabit link as 1.
So if a router sees 2 paths, one 1 Gbps and one 10 Gbps, it sees both costs as 1, and the path selection becomes arbitrary, or relies on secondary factors, undermining the core principle of path optimization.
Exactly. OSPF's intelligence is artificially capped by an outdated default. The practical reality for anyone deploying OSPF today is that you must adjust that reference bandwidth upward, say, to 1000 MEPs for gigabit networks, or even higher for 10 gigabit environments, to ensure OSPF can accurately differentiate between high-speed links and select the truly shortest, highest capacity path.
So it's a manual setting that carries massive weight.
Massive weight and path calculation. You have to get it right.
We've established that OSPF is a sophisticated, decentralized map maker. But map making on a massive scale requires organization, hierarchy, and specialization.
You can't just have chaos.
Our sources clearly show that OSPF isn't a flat protocol. It uses specialized router roles and the concept of areas to manage complexity and information overload.
And managing scalability is the driving force behind the OSPF design. If you had one gigantic LSDB covering thousands of routers, any small change would trigger a recalculation on every device.
A broadcast storm.
A catastrophic scenario known as route instability. By segmenting the network into areas, we contain the scope of the LSDB and introduce specialization to manage the traffic between those areas.
Let's break down the key router roles, starting with the mandated central nervous system, the backbone routers.
Backbone routers operate exclusively within Area 0. This is the central mandatory area, often called the core of the OSPF domain.
The absolute core.
And every other area must connect logically or physically to Area 0. The backbone routers are responsible for distributing the summarized routing information that binds the entire OSPF domain together. Area 0 is the non-negotiable meeting point.
And then we have the necessary boundary agents, the area border routers, ABRs. They are the official gatekeepers.
They absolutely are the gatekeepers. An ABR is defined by having interfaces in more than one area, and they must always have an interface connected to Area 0.
Always.
Their function is twofold: summarization and filtration. They take the vast amount of detail from a non-backbone area, let's call it Area X, and summarize it efficiently before injecting it as inter-area routes into Area 0. They use Type 3 LSAs for that, which we'll get to.
So they're the traffic managers.
They are the traffic managers and librarians responsible for controlling the flow of information between areas.
So if a router in Area 5 needs to talk to a router in Area 8, the data has to pass through the ABRs in Area 0.
Correct.
Area 0 is the hub, and the ABRs are the spokes connecting to it.
That's the rule. And then we have the specific role for connecting outside the OSPF domain entirely. The Autonomous System Boundary Routers, ASBRs.
The ASBRs are the translators connecting us to the rest of the world.
They are the designated routers that bridge the gap between OSPF and external routing protocols such as RIP, EIGRP, or the ubiquitous BGP, which manages routing across the public internet.
So if your organization uses multiple protocols,
the ASBR handles the vital function of redistribution, taking routes learned from those external sources and translating them into the OSPF language so the internal map makers can understand them. They are literally the defining boundary of the entire OSPF autonomous system.
okay, moving inside an area, we also have the specialized roles of the designated router, the DR, and backup designated router, the BDR. What is their specific context?
The DR and BDR roles are only relevant in multi-access networks.
So Ethernet.
Typically standard Ethernet segments where many routers share the same broadcast domain. Imagine multiple routers plugged into a single switch. The necessity arises from the overhead problem.
Ah, the N-squared problem.
If you have 20 routers on one Ethernet segment and every router tries to form a full adjacency with the other 19, you create a requirement for 190 adjacencies. That leads to a massive self-inflicted flood of OSPF hello packets and LSA traffic on that single link.
That would bring the network to its knees. So the DR and BDR are elected specifically to solve that exponential scaling issue.
Exactly. They centralize communication. The DR and BDR are elected to reduce OSPF traffic. Instead of forming 190 adjacencies, all 20 routers, the other 18 are called D-routers, only form full adjacencies with the DR and the BDR.
Much more efficient.
The D-routers form 2 adjacencies, and the DR-BDR form 19 each. This significantly cuts down on the necessary connections and the resulting protocol overhead. The DR takes responsibility for generating the crucial Type 2 network LSA for that segment, ensuring everyone stays synchronized efficiently.
And the BDR.
The BDR is passively waiting, instantly ready to assume the DR role if the primary fails, guaranteeing no disruption to synchronization.
That makes the structure clear. The roles define the chain of command. But if the LSDB is the map, the link state advertisements, LSAs, must be the granular language OSPF uses to draw that map.
They are the fundamental messaging system. LSAs are the data packets that detail the state of links, network segments, and external routes. Understanding the 5 core types mentioned in the source is critical because they dictate the flow and containment of information.
Let's start with the most local, the self-reporting detail. Type 1 router LSA.
Type 1 is the self-portrait. It is generated by every single router. It describes the router itself, its directly connected links, the status of those links, and their current cost within its local area.
So it's contained.
The key takeaway here is its scope. This LSA is strictly confined to the area in which it originated. It is the core building block for intra-area communication, the data needed to calculate paths inside the immediate neighborhood.
Next, we have the neighborhood directory, Type 2 network LSA.
Type 2 is generated exclusively by the designated router, the DR, on those multi-access segments we just discussed. Its purpose is to describe which specific routers are connected to that shared segment.
Okay, so it's a roster.
It's like a directory for that local segment. And like the Type 1, the Type 2 LSA is also strictly restricted to its area, ensuring local knowledge doesn't leak unnecessarily.
Moving up the hierarchy, we need to connect the neighborhoods. That's the function of Type 3 summary LSA.
This is where the ABRs earn their money. Type 3 LSAs are generated by the area border routers. When an ABR learns a set of routes from Area X, it generates a Type 3 LSA to advertise those routes into the next area, usually Area 0, the backbone.
This is how routers learn about inter-area routes.
Yes, routes that exist elsewhere in the OSPF domain. The efficiency of the entire OSPF system hinges on ABR summarizing these Type 3 LSAs effectively, preventing individual host routes from Area X from flooding Area 0.
So Type 3 is how we bridge the different areas inside the OSPF kingdom. What about the news coming from entirely outside the kingdom routes from the wider internet or other protocols?
That's the critical role of Type 5 external LSA. This LSA is generated by the Autonomous System Boundary Routers, the ASBRs, when they perform redistribution. They advertise routes that have been explicitly learned from another routing protocol, like RIP or BGP, and brought into the OSPF system.
And these go everywhere.
Type 5 LSAs are the standard way to carry these external routes, and they propagate across the entire OSPF domain, traversing Area 0 and continuing into standard non-backbone areas.
And finally, we hit the special case, the exception that proves the rule. Type 7 NSSA LSA.
The Type 7 LSA is a product of necessity. It's a specialized LSA used to carry external route information, but only within a very specific context, a not-so-stubby area, or NSSA.
Which we'll get into.
We will discuss these areas in detail later, but the simple fact is that stub areas block standard Type 5 external routes. But what if you need an ASBR inside a stub area? You can't use a Type 5.
You need a messaging system that allows the external data in, but is temporary and doesn't conflict with the standard Type 5 filtering.
Exactly. The ASBR in the NSSA encapsulates its external routes into a Type 7 LSA. This Type 7 LSA is allowed to propagate within the NSSA. The crucial mechanism is that when this Type 7 LSA reaches the area border router,
The ABR translates it.
the ABR acts as a translator, converting the Type 7 LSA into a standard Type 5 LSA before injecting it into Area 0. This allows external routes to originate deep within a restricted part of the network without violating the core principle of area filtering.
Before any of these intricate LSAs can be exchanged and the map built, the router has to establish a reliable, trustworthy relationship with its neighbor. This process forming an adjacency is not instant. It's a precise, multi-step handshake with 7 distinct states.
And this sequence is the formal agreement between two routers. It ensures they agree on the rules, they're speaking the same OSPF dialect, and most importantly, that they have fully synchronized their databases before they start routing production traffic.
State 1, the very beginning, is the passive state, down.
Down is the initial state, sometimes humorously labeled Z's in diagrams. The router has not sent or received any OSPF hello packets from a neighbor on that interface. It's essentially waiting for someone to knock on the door.
The first knock is state 2, init.
In init, the router has received a hello packet from a neighbor, establishing a one-way communication link. The current router knows the neighbor exists and knows its router ID.
But the neighbor doesn't know about me yet.
Critically, the neighbor hasn't yet seen the current router's hello packet or hasn't processed it in a way that acknowledges mutual awareness. The connection is still unilateral.
State 3, two-way, is the establishment of mutual stable recognition.
This is the first significant milestone. In two-way, the router sees its own router ID listed within the neighbor's hello packet.
So it's mutual.
It confirms that the neighbor knows it exists and has accepted the relationship parameters. They are now officially mutual neighbors. And this is the critical juncture on multi-access networks. The DR and BDR election occurs immediately during this state.
They decide who's in charge before moving on.
Right, they determine the spokesperson for the segment before continuing the data exchange.
So once they know who they are, and if necessary, who's in charge, they need to decide